So welcome back, everyone. Today, we're actually going to be doing a bit of a recap video of the collinearity, per se, of span of sets of vectors and their independence and or dependence. So today is just going to be a summary of those two concepts in one long video or multiple parts. So one long part series, per se. So let's get started. So let's first establish a set of vectors. Going to be, because this is going to be either a long series or a long video, the set will be of three-dimensional vectors. So let's say we have -4, 7, 6. Then we have 2, 6, 4. Then say 1, 3, 4. Okay. And what we want to know is if the span, let's say this is V1, this is V2, this is V3. The span of vector 1, vector 2, vector 3, we can put an arrow above them to signalize that they're column vectors. So we're asking, is the span in the three-dimensional real value, or in other words, do these three vectors span the entirety of the three-dimensional, not a plane, but of the 3 dimensions, the entirety of the real 3 dimensions. So essentially, this ties into linear independence or dependence. If it's dependent, then it probably won't span the entirety of R3. However, if it's independent, then it definitely will span the entirety of R3. And our second question is, again, this is also tied into this. Is it Indep, independent / dependent? So yeah, basically asking, is it independent or dependent? So let's start off by trying to answer the span question. So for span, we assume that essentially it's just solving a system of equations, because what we want to do is we want to prove or disprove that this system of 3 vectors spans R3. And the way you do that is by solving a system of 3 equations with 3 variables. In this case, we can use C1. Let me just write this out to make it look less confusing. So C1 times -4 plus, so we're looking at linear combinations here as well, plus C2 times 2, 6, 4, plus C3 times 1, 3, 4. And to prove this, we have to set this equal to some random values, some random x vectors. So we'll say x1, x2, x3. Right? So essentially you're saying that we're trying to figure out the values of C. We're trying to provide a formula for which, if somebody were to give us these values of x, we'll be able to provide them with a constant C1, C2, and C3. So that to show that any value that's given here, you can provide some linear combination of these 3. And if we'll see, but if this is actually, we can still make this statement even if these vectors are dependent, right? Because we'll actually get a undefined section, but I guess in the next video I'll show you an example of that, but we'll see. So firstly, we want to use, I'm going to use Gauss elimination. It's probably the most simple way of doing so. Gauss-Jordan elimination specifically. So let's put these column vectors into a 3x3 matrix. One, three. Sorry, that looks like a negative. 1, 3, 4. Oh, oops. This is an augmented matrix, right? We're making our augmented matrix. Here we have the values of x. So x1, x2, x3. This is where it can start getting confusing. So essentially, we want to convert this now into reduced row echelon form. So these values have to be the diagonal values. So these values, they have to be all ones, while these values here have to be 0. So all the values above those ones, or better called pivots. Okay, so first operator, let's see what we can do. So let's start off with getting, what I usually do is I start off with getting this to be a 0. So I'm going to see if I can divide this. I should be able to. So point 7. This might get a little difficult. Okay, so we have that. We have 1.75. So what we want to do is we want to multiply this. We want to multiply row 1, 1.75 times row 1. You can see how this will begin to get really tedious. And then add to that. Actually, let's see if this might give us a easier solution. No, it won't. Never mind. Plus row 2, and our changes go to row 2. So let's do that. So 2 times 2 times so how could I do this for you? So 2 times 1.75, that's just equal to 3.5, I think. Should be that. 3.5. Okay, so that's equal to 3.5. So we can erase that. So we want to change this matrix now. This remains unchanged. Okay. So obviously this becomes 0 now. So we don't have to worry about that, thankfully. Then 3.5 plus 6 is just 9.5. Because look, we're multiplying 2 by this value here and then adding to that this. So 9.5, right? 9.5, I think so. And then multiply, okay, so that's going to make it easy on us. 1.75 plus 3 is just 4.75, just like so. 1.75 times x1, so that's 1.75 times x1 plus x2. So there we go, that's our first row done. We can actually we can actually do 2 steps in a row. You can tell this is just going to get so tedious. Trying to see if I can improve this situation. Yeah, this is the only problem with this version. Well, it's actually going to be universal either way. So we can erase this just to save some space. And then what we can do now is, firstly, I'm going to get rid of this work in a second, but we can do 2 steps at the same time. Okay, this isn't that bad. So negative 2.5. So we don't have to multiply by negative actually. We can just multiply this top row again. So what we can do is we can do this. We can multiply row 1 by 1.5 and then add to that row 3. And changes go to row 3. So let's do that. So this becomes 0. And then 1.5 times 2, well, that should be 3. 3 plus 4 is 7. 1.5 plus 4 is just 5.5. 1.5 plus 4 is just, yeah, okay, 5.5. And then 1.5 times x1 plus x3 is just obviously 1.5 times x1 plus x3, literally. Okay, so we're doing well. We've already got 2 of these pivots. We've already got 2 of these zeros. But we still have a pretty long way to go. So what I want to do now, oh no, we still have horrible values. Okay, well, we can just, oh no, this is not going to be fun. Oh gosh. That's going to be a big problem. Or maybe not. We'll see. Yeah, you can already tell this is just getting horrible. This is just horrible. So 9.5. Lots of arithmetic. Four. 3. Oh no. 7, 6, 5. Let me put this to the side. Oh, this is, how's this? Okay, 8. No, 7. Okay, this is just not interesting. 9. We can just approximate it. Let's just approximate it to 1.3, because this is just horrible. So 1.3, approximately, so. The problem is, here actually what we can do is let's just divide row 2, because I picked this problem on the spot, so row 2, divide that by 9.5. Might regret this in the future, but changes go to row 2, obviously. So let's just do that real quick. So let's not worry about estimating. It's horrible. Okay, well we can just keep this in our head. We don't have to write that there. We need room anyway. So now our new matrix, augmented matrix, is this. So obviously these row 3 is the same. 5.5. Actually, it might be. I need to think critically here. It might be easier if I just divide. It might be. Yeah, might. Yeah, I'm going to do that. We're actually gonna divide row 3 by 7. Should be easier. Definitely, yeah. So we get 1. We can keep this. This is a mess. We'll definitely split this up into multiple parts. Oh man. Okay. So 5.5. We could just like do something like, we'll keep it like that for now. Okay. Because what I did was I multiplied both the top and bottom by 10. So I didn't have to have a decimal place there. Anyway. We don't have to worry about this value for now. And this becomes 1/7 times that, 0.5, x1 plus x3. Okay. Oh man. Okay, so now we can just multiply. Now we multiply negative 9.5 times row 3 plus row 2. Changes go to row 3. Okay, I need lots of room here. Okay, so what we get here is we get row 1 stays unaltered. Okay. Row 2 stays unaltered as well. Oh no, we're gonna have to write this here. Okay. Gonna move this out of the way. Obviously, we still get 0 here. We get 0 here. And so we're multiplying by negative 9.5. Oh, negative 9.5. Okay. Going to have to do some basic arithmetic here. Okay, this part won't be that difficult, thankfully. Okay. So 55 times... just going to do some arithmetic. 37. Oops, that's wrong. It's 47. 47. Okay. Just check this, because if I make a mistake here, then that could be very costly. Okay, so it's negative, so we get that. And it's negative, so here we get 52.5 over 522, negative 522.5 over 70. Okay, great. And then what we can do here is we can also just do negative 9.5 over 7 times 1.5 x1 plus x3. Okay, that was relatively simple, thankfully. Let's get rid of this arithmetic. Okay, well, now to get one pivot here, we're going to have to divide both sides by this value here. Now, that's not as bad as you would think. Let's be honest, it's still pretty bad. Oh wait, we'll be able to cancel terms. Yes. Okay. This is great. So now we're essentially dividing row 3 by this value here. So let's do that. And obviously, we're multiplying by its reciprocal. It's equivalent. So let's do that. Firstly, we're just going to zoom in on this problem. We'll cancel the negatives, which is nice. So we'll have 9.5 over 7, negative 9 times 522.5 over 70, but we can cancel that. Perfect. And then we get 10 here. And then I think I'd rather actually move the decimal place further back one. Oh no. Sorry. So we can make that decimal place non-existent now. Actually, sorry, that's incorrect. And just undo that. So essentially you're just dividing this by 10. So you get, yeah, that's better. Okay. Just gonna get rid of that. So you get this to the side. Erase this. Sorry, I'm still getting the hang of this technology. 52.25, right? And then you just get, it's self-explanatory. The negatives cancel out, obviously. So we don't have to worry about this. Just have to worry about that. So it's just positive 9.5 over 52. And then we can actually just multiply both the top and bottom by. So this is our result. This is our result. Technically, yep. Just make sure, so that cancels out to 10. Yeah, it should be right. Okay. So now, what we want to do is we want to plug in this value for this, so it becomes -4, 2, 1, x1, 0, 0, 0, 1, right? 95 over 52.25 times, actually what we can write here is just, oops, we've actually gotten our value of C3. So C3, we now know, is equal to, C3 is equal to, let's see, C3 is equal to 95 over 52.25 times 15 x1 plus x3. And this is really useful because this will make our process a little much easier, actually. Okay, so now we have 9.5, 4.75, and then 1.75 x1 plus x2. Okay, great. So now we've gone past the first hard bit. Oh wait, actually, this won't be as bad now, theoretically. Yeah. So now we can actually, what we can do now, we'll revisit this soon, probably help to underline that at least. What we can do now is actually we can, let's see, we can multiply row 3, let's write this out, we can multiply row 3 by -4.75 times row 3 plus row 2. Changes go to row 2. So let's write this out now. And then we might be able to to multitask here. I'd rather not, since we have these annoying values here. So we can, so this is going to be rather straightforward. We get -4, 2, 1, x1. Going to make this decently large. And we get 0. Obviously this will be the same here, C3. So -4 times row 3, so we have, this becomes a 0. This remains 9.5, right? And then here we'll get basically this value, 1.75x1 plus x2, in parentheses, plus -4.75 times C3. Right, you can kind of see that. Oh, and we're actually done with that row now, so we can get the value of that. Now all we have to do, and it's fine since we're using C3, since you can actually work from the bottom here and it'll be valid. So we can get, yeah, this is getting more tedious than I expected. Thankfully we are on the home stretch though. And what I want to write here is just, so we're essentially dividing both sides by 9.5, so we get C2. And we'll write out C2, our answer for C2, using some basic arithmetic. C2, okay, so we have 1.75 x1 plus x2 minus 4.25 C3, 4.75 actually. .75 all over 9.5, or in other words you can put times 1 over 9.5, right? Okay, that's our value C2. Now we want to find our value C1. So we're very close, actually. We're very close. We only need 2 more values to get our value of C1. Okay, so here what we can do is we can actually subtract these 2 rows here. So we can subtract row 3 from row 1. We get our new row 1. Then we'll get another 0. So that's great. Okay. So we get, look at all of these matrices. It's amazing. I'm really passionate for this stuff. Okay, so these should remain the same, right? -4, 2. This will become 0. We have 0, we have 1, we have 0, we have 0, we have 0, and we have 1. Then we have x1, c1, c2, c3. Okay, great. Now we can actually multiply this row by -2. Or actually, easier method would be to again use subtraction. Oh, whoops, I did something wrong here. That could have been bad. That's minus C3. Okay. So now let's multiply. So we can do R1 minus 2 times row 2. Okay, R1. Okay, so let's do that. So, nice. Okay, we can multiply this by -2. That's the same thing. So we get, let's first write out the matrix. So -4, and we get 0 here. First, let's write this part out. And then all we have to worry about is this section here. So it would just be -2 times C2 plus row 1. So that's basic. That's just x1 minus C3 minus 2 times C2. Now it seems a little bit awkward that we're working down from C3 to C1. That's fine. And we get C2, C3. Okay, now final step. Divide both sides by -4, and we get 1, 1, 1. This might seem familiar if you watch my past videos. This is reduced row echelon form. So you divide both sides by -4, and you get -1/4 times x1 minus C3 minus 2C2. Okay, great. This is obviously just going to be C2 and C3. Okay, great. So now we have it in terms of C, and we can finally get our value of C1, which is, you have to scroll all the way up, -1/4 times x1 minus C3 minus 2C2. x1 minus C3 minus 2C2. And there we go. So now we've essentially just proven if you give us any value of x, even though this might seem it's in terms of C, I'm assuming that you start from calculating for C3. So somebody gives you values of x, then you can plug those values of x back in when you get C3, but you also have to include C3 in this equation here. It's going to be very tedious to calculate, obviously, but nevertheless, you'll get your answer. So we've just proven that this can span any vector. So if you give me the coordinates of a given vector, the x1, x2, and x3, then I can give you the linear combination of this set of vectors, proving that this set of vectors does span R3. Okay, well, that should be enough for today's video. I'll make a part 2 regarding the independence/dependence of this set. So hopefully enjoyed, and yep, that required a lot of brain cells, so thanks for watching.